In this question, we have two small charged spheres hanging from cords of equal length L, and they make small angles θ1 and θ2 with the vertical. The charges and masses on both the spheres are given, and θ1 and θ2 are assumed to be very small. Now the first question is to determine the ratio between θ1 and θ2. Now if all the angles to the vertical are assumed to be small, which is already given, then the electric force of repulsion will always be horizontal. And we can take small angle approximation here, which says that for small angles tan theta is equal to sin theta is equal to theta. Now let's draw the free body diagram of these two masses. So for the first mass, the free body diagram will look like the gravitational force acting downward given by m1 times gravity, the force of repulsion which will be away from the other mass, and so in this direction. Let's call this as F, electric force 1. And there is a third force which comes due to the tension on the cord, and this will be in this direction. Let's say this as Ft1. Now since the cord makes an angle θ1 with the vertical, this force should also be at an angle θ1 with the vertical. Now let's draw the free body diagram of the second mass. So over here, as we drew the free body diagram of the first mass, in this case also, there will be a gravitational force m2g downwards. There will be a force of repulsion, let's say Fe2, away from the first mass, and then there will be a tension force, say Ft2, acting at an angle θ2 to the vertical. Now, since the spheres are in equilibrium, we can say that the net force in each direction is 0. Let's take the right to be positive horizontal direction and up to be, this is positive horizontal, and up to be positive vertical. Or let's say this in terms of coordinates. Let's mark this in terms of coordinates. So this will be, say, positive x-axis, and this will be our y-axis. Now again, since the masses are at equilibrium, so the net force in each direction should be 0. Now let's find the net force on the first particle along x direction. This will be equal to Ft1 times sin θ1, which is the horizontal component of T1, minus Fe1, because they are in opposite direction. And this should be equal to 0. And this gives Fe1 is equal to Ft1 sin θ1. Similarly, the net force on the first particle in y direction should also be equal to 0, and this is ft1 cos theta 1 minus m1g equals to 0, and this gives me ft1 is equal to m1g over cos theta 1. Now, plugging this value of ft1 into this equation, we get fe1 to be m1g over cos theta 1 times sin theta 1, and this gives me m1g times tan theta 1. Now, using our small angle condition that we described here, we get this force Fe1. Let's write this nicely. Fe1 to be equal to m1g theta 1. Let's call this as our equation 1. Now let's do the same thing for the second mass m2. So for the second mass, the net force along x direction, which is equal to the electric force of repulsion, or the force of repulsion on the second mass due to the first mass, minus the component of the tension force along x direction, which is sine theta 2, and they are in opposite direction, as you can see from here. So this should be equal to 0, and this gives me Fe2 is equal to Ft2 times sine theta 2. Similarly, let's do this fast. F2y is equal to m Ft2 cos theta 2 minus m2g, and this should be equals to 0, and this gives F22 is equal to m2g over cos theta 2. Now we can similarly plug this value in this equation, and we get Fe2 to be m2g tan theta 2, and this is equal to m2g theta 2 using our small angle condition. Now let's call this as our equation 2. Now since the Fe1 and Fe2 are the forces of repulsion on mass m1 and on mass m2 because of each other, so they should be equal. That means Fe1 should be equal to Fe2, and this should be equal to K Q1 Q2 over d square, where d is the distance between the two masses. Now let's use this equation Fe1 is equal to Fe2 in our case. So if Fe1 is equal to Fe2, then from equation 1 here and equation 2 here, we get m1g theta 1 should be equal to m2g theta 2, and this gives theta 1 over theta 2 is equal to m2 over m1. Now in this case, our m1 and m2 are equal to m. So theta 1 over theta 2 will be simply equal to 1. So this is our first part. Now in the second part we have to find the horizontal distance between the two spheres. That is, we have to find the distance d here. Now using the small angle approximation again, we have this distance d can be given by L times sine theta 1 plus, which is this small distance, this part, plus L times sine theta 2, which is from this line to the other sphere. And since sine theta 1 is equal to theta 1 by small angle condition and sine theta 2 is theta 2, we can say this is equal to theta 1 plus theta 2. Let's write this in the next page now. So we get our d equal to L times theta 1 plus theta 2. But in the first part we already got theta 1 is equal to theta 2 because the ratio is 1. So this gives our d to be 2 times L times theta 1. Now the force of repulsion between them, let's say Fe1, which is also equal to Fe2, is given by K Q1 Q2 over d square as written over here. And Q1 and Q2 are given as Q and 2Q respectively. So this will be equal to 2 times KQ square over d square. But we have one more equation to use over here, equation 1, where Fe1 we found as m1 times g times theta 1. So this is equal to m1 times g times theta 1. And this gives me 2k square over m1g theta 1 equals to d square. Now we can solve theta 1 in terms of d1 using this equation. So we get theta 1 is equal to d over 2l, and we can use this value over here in place of theta 1. And this will give me d cube is equal to 4k q square l over m1g. And m1 here is equal to m2 and is equal to m. So d cube is equal to 4k q square l over mg. And hence d will be equal to 4k q square l over mg cube root. So this is the distance between the two spheres 1 and 2.